In this video, we'll be starting chapter 5 on right triangle trigonometry. And the main things we're going to be learning in this chapter is how to solve triangles. So we'll start with right triangles, review properties, and discuss rules such as SOHCAHTOA, and how we can apply them to solving various word problems. And then in sections 3 and 4, we'll expand our ability to solve triangles which are not right triangles using what we call the law of sines and the law of cosines. Um, so to begin with, let's start with section 1, which is on right triangle trigonometry. So basically, this is an alternative definition to the trigonometric functions. Many people refer to this as SOHCAHTOA, and this is how a lot of people learn trigonometry. I remember in high school, this was one of the main rules that I remember, but I didn't really necessarily learn it the same way we did in chapter 4. So what I wanted to do in this video is kind of talk about SOHCAHTOA, how does it work, what does it mean, and then also why. Why does it make any sort of sense? But let's start off with the rule SOHCAHTOA and what we often refer to as the trigonometric ratios. So if we are dealing with a right triangle, and like instead of just dealing with the side lengths, we're also focused on the angles within the triangle. So let's say we have a particular angle of the triangle, just call it theta as an arbitrary one of the angles, but you could also be dealing with the other angle. But basically, when we're talking about an angle, we refer to the sides of the right triangle very specifically based on which one is attached to the angle. So first of all, the hypotenuse is always the largest side of the right triangle, as we know. Like when we're doing the Pythagorean theorem, a squared plus b squared equals c squared, hypotenuse is always c, which is always the longest side. And also another way to remember it, if is it should be always across from the right angle. So wherever the right angle is in that triangle, hypotenuse should be across the triangle from it. But anyways, notice that whether I'm talking about this theta or this theta, the angle that we'll be looking at or observing within a right triangle should be always attached to the hypotenuse. But also there's another side of the triangle. We sometimes refer to the other two sides of the right triangle as the legs. So we have the hypotenuse and the legs, but specifically when we're talking about an angle, one of the legs is attached to the angle, which we often refer to as the adjacent side, where the other side is across the triangle from that angle, which we refer to as the opposite side. So with all that being said, that's the trigonometric ratios is an alternate definition of the trigonometric functions as a function of the angle. And each trigonometric function gives us a unique ratio between two of the three sides of the right triangle, where sine of theta is defined to be the opposite side over the hypotenuse. So basically, let's say the adjacent side was 5, the opposite side was 2, the hypotenuse was 8. Okay, that doesn't make sense, but just, whatever the numbers are, sine would take whatever the opposite, the sine of theta should be equal to that ratio besides, say, 2 to 8, or whatever those two numbers are, always. And another thing you might be wondering is, well, why? I'll want to get to that in a minute, but let's just kind of discuss what we call SOHCAHTOA and the rules. And really, the moniker SOHCAHTOA is a way of remembering these trigonometric ratios because sine is equal to opposite over hypotenuse. Cosine, adjacent over hypotenuse, basically whatever this side is divided by this side should be equal to the cosine of the angle theta. And the tangent of the angle theta is always going to be equal to the opposite divided by the adjacent side in the triangle. And after all that being said, notice that we have our three other functions as well, cosecant, secant, and cotangent. And I'd remind you that each one of those, as before, is the reciprocal of sine, cosine, and tangent. Because one thing I wanted to make very clear, these definitions are not really different than the way we did it before, using the unit circle in chapter 4. Like sine, we said sine is y, cosine is x, tangent is y over x, and so on. But notice that, as we talked about before, sine and cosecant, those are reciprocal functions. Notice that that is also true amongst the trigonometric ratios. So if you memorize SOHCAHTOA, and if you know which trig functions are reciprocals of one another, you can remember, well, the reciprocal of sine is cosecant, which would be h over o. And so you could kind of remember the reciprocal functions as cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. But so you could say SOHCAHTOA if you wanted to remember it. It's a little, it doesn't have quite as nice of a ring to it as SOHCAHTOA does, which is why I don't really recommend you try to memorize that. And also, as I said before, those three functions are less important than sine, cosine, and tangent. Those are the three main ones, and that's why really those are the ones we care about most. And another point is that actually, since our calculator, most calculators typically have sine, cosine, and tangent, those are usually the only three we really need to worry about, because the other three are just redundant. We're solving triangles, and we don't really need them in general. Technically, we could still use them, but as we talked about with inverse functions, we've defined this arcsine, arccosine, and arctangent. I sort of said, well, don't really worry about the other three. Well, you could define the arc cosecant and arc secant and arc cotangent. It's not really necessary because basically they're just the same ratios. They're just reciprocals, so they're kind of redundant anyways. And another thing that I want to emphasize, these definitions only work with right triangles. So if the triangle does not have a right angle, immediately throw all this out the window. SOHCAHTOA does not make sense anymore. And we will be discussing how you solve triangles which are not right, but that's a little bit more difficult, and we're going to derive some formulas for doing that in 5.3. But anyways, SOHCAHTOA is helpful for solving triangles, and basically it's kind of like it sets up an equation where if I know two of the sides of a triangle, I could find theta, or if I know one angle and one side, I could find the other unknown. It sort of like opens up a new formula that relates two of the sides of the triangle to the trigonometric function of the particular angle that we're referencing. And also, just as a to mention, if we were to switch the theta up here instead of down here, just if you use your imagination, that would switch which sides are opposite and adjacent, because it always has to do with, well, what the adjacent side is always attached to the angle that you're focusing on, and the opposite is always across the triangle. So basically, the geometry of where they are, it's not always going to look exactly like this, but it's more about specifics. So let's do a couple examples of solving right triangles using SOHCAHTOA, and we'll move to the packet as we do this. But actually, in the slides, I have a link to, if you've ever wondered, the Pythagorean theorem is another theorem which is true for all right triangles, a squared plus b squared equal to c squared, which we're going to be using also to help us solve these triangles. But if you've ever wondered, well, why is this true? This is a very fundamental formula in a lot of trigonometry, right? Back to circles in the unit circle formula. I actually posted a video about that a few years ago, and walked through one particular proof. There's actually a bunch of different ways people have proved it's true, but it's another formula for right triangles, which we use quite a bit when we're working with trigonometry. But let's do an example of solving a triangle from the packet via SOHCAHTOA. So let's just say we are dealing with this right triangle right here. We're given a triangle. Again, it has to have a right angle in it, which is marked here. But we're told that this side of the triangle is 3, this side is 4, and we're asked to solve the triangle. And also, from here on out in chapter 5, if I ever ask you to solve a triangle, it's important that doesn't just mean find the third side, because usually, back in high school math class or whatever, the goal, usually if they say find the third side, that's what we're trying to do. But solving a triangle means not only solving the three sides of the triangle, but also finding all the angles of it. So like, notice since theta is marked, our goal is also not just to find the unknown side, but also what are the interior angles of the triangle. And my point is, we can use SOHCAHTOA to do all of this. But first of all, given that I have 2 out of 3 sides, we can always solve the third side via Pythagorean theorem. So I could call it a squared plus b squared equal to c squared, but another thing is I could label these as, this would be the adjacent side, and this would be the opposite side to angle theta. And the side across from the right angle is always the hypotenuse. But I could say that as a squared plus o squared is equal to h squared. Because, that's the same as a squared plus b squared equals c squared. The hypotenuse is always c with the Pythagorean theorem. Or, plugging those numbers in, I would have that 4 squared plus 3 squared is equal to the hypotenuse squared. Of course, that would be 16 plus 9, which is 25. And then taking the square root of both sides and ignoring the negative solution, we would have that h is equal to the square root of 25, which is, of course, 5. And algebraically speaking, technically it could be plus or minus 5, but obviously since it's a physical triangle with physical lengths of the sides, it should be a positive solution. So anyways, we can find the third side via Pythagorean theorem always. Again, with the right triangle, that always works. And if it's not right, another thing about it, I don't know if you've ever wondered, well, how do I find the third side of a triangle if it's not a right triangle? Again, that takes a little bit more work. It's not quite as simple. But anyways, now the other question is, well, how do I actually find the interior angles? I know this is 90, but how do I know what these two angles are? But that's that's where SOHCAHTOA comes into play. Because if I know the sides of a triangle, I could use the trigonometric functions to find those angles. Because for instance, we now know that the sine of theta is equal to the, and again, remembering the moniker SOHCAHTOA, sine is equal to opposite over hypotenuse. Well, I know opposite is 3, hypotenuse is 5. So sine of theta should be equal to 3/5. And notice that this gives me an equation where the only unknown is theta. And I could solve this equation by using the arcsine function. And that's one of the main purposes of the inverse functions. We didn't really get into this because we hadn't gotten to SOHCAHTOA yet. But the reason why trig inverse functions are so useful is they can figure out theta, right? Because if I apply arcsine to both sides, that would leave me with, well, theta must be equal to the arcsine of 3/5. And while we talked about how you can evaluate these sorts of things on a without a calculator using the unit circle, this particular example would not. I couldn't solve this on the unit circle because what I'm kind of wondering is, well, what angle has a y value of 3/5? Because sine on the unit circle is always correspondent to y. But 3/5 is not a value that we have on the unit circle, right? The unit circle consists of fractions like 1/2, √2/2, √3/2. It all has very specific angles, 30, 45, and 60 degrees. But if it's any other angle, like in this case, our unit circle is not going to be very helpful in actually determining, so what is the specific angle for this specific trigonometric ratio? And ancient trigonometry was way more focused on ratios and angles, and this is a lot more similar to what would be on ancient, say for example, the ancient Babylonian tablets. But they didn't have they didn't necessarily have an exact way of measuring this. They used protractors and stuff to do these calculations. But we can use a calculator to find this answer. That's kind of the value of having calculators that have inverse trig functions on them, is we can get a fairly well, it's not exact, but it's a very good approximation to what the angle would be. And my recommendation is to use degree mode. It should say this in the packet, but if I'm in degree mode, when I'm using my arcsine function here, it will give me an angle in degrees. And typically, when we're solving triangles, we want to know this angle in degrees. That's just usually the way we answer angles in the context of architecture, vectors, trigonometry. You could still use radians, but since, most of the time when we're doing applied problems, we use degree mode instead, because that's what the average person would understand ahead of radians. But anyways, what I come up with here is that the interior angle of that triangle, angle theta, is approximately 36.9 degrees, just rounding to the nearest tenth arbitrarily. And like there we have it. It should kind of make sense to the context of the triangle. While this triangle wasn't exactly measured out, it was just something I put in the packet. A triangle which has a 3 to 5 ratio of the sine must have an angle of approximately 36.9 degrees. And if you actually take a ruler and you actually measure out and make your own triangles, this is a fun activity for you to do. Well, fun activity to try if you are a little bit skeptical, or you kind of having a little bit, if you're a little bit confused about how all this is working, you can actually make a triangle, use a ruler, measure out one length 5, one length 3, connect them together with a straight line, and measure it all out. You'll see that it should add up exactly right. If this is like 3 inches and 5 inches, you'll see that the connecting leg is 4 inches, and if you take a protractor and measure the angle, you should get about 37 degrees as well. So that's basically how it was done historically. Instead of they didn't have calculators to figure out what the arcsine of 3/5 was, but they used smaller triangles to figure these out. And then once they knew the base ratio, the approximate angle, they could apply that to larger scale triangles, such as building a pyramid or whatever. Anyways, another thing you may have been wondering there is, why did I use the sine? But the point is, if you know all 3 sides of a triangle, you could actually use any trigonometric ratio to find the angle. Like, for example, I could have also used the cosine function, because cosine of theta, if again remembering the moniker SOHCAHTOA, cosine is always defined to be the adjacent side over the hypotenuse, or in this case 4/5, because the adjacent is 4 and hypotenuse is 5. And in exactly the same way, I could find theta by taking the arc cosine of 4/5. And this should always be the same answer as this one, because it's coming from the same triangle. So I should be getting the same answer when I do this. And we can always check what is the arc cosine of 4/5. But notice what I do is what I get is the same thing, because really I'm solving the same angle because it's correspondent to the same triangle. And let's say I was to use the tangent function, SOHCAHTOA, tangent is opposite over adjacent 3/4. And if I want to find theta, theta should be equal to the arctangent of 3/4. But notice that no matter which way I decide to solve this, all of these methods help me identify the interior angle of this triangle, which is going to be the same no matter which way I do it. So each ratio, if you're wondering, well, why do I need to know all of them? Notice that even if I had not solved the hypotenuse, I could have still found the angle using just the arctangent, because as I was presented with this information, all I had was 3 and 4, opposite and adjacent. So basically, if I was trying to solve this problem efficiently of what is this interior angle, I could have just used the tangent function to start with, because I didn't have the hypotenuse. Or let's say we had just the adjacent side and the hypotenuse side. We could have used the cosine to start. And that's really the point of each of these functions. The difference is it's a different ratio of the triangle, so whatever information I know, I could use that specific function to do it. So what I'm kind of getting at is, how do I know whether to use sine, cosine, or tangent? It just all depends on what you know. Which of the 2 sides do you know, or which are you trying to figure out? And we'll do more examples in the next video of solving with SOHCAHTOA. And to wrap this video up, the last thing I wanted to get into is, well, why? Why are the trigonometric ratios true? How does this have anything to do with the definitions that we looked at earlier in the semester? So what I wanted to do is just back up to the previous slides when we talked about the definitions of these functions. And I wanted to compare, and contrast. What are the differences, and why are these so different? Like, if we look back to how we defined it in chapter 4 based on the unit circle, we defined sine of the terminal point, where t is the distance from the initial point to the terminal point, to be the y value, cosine to be the x value, tangent to be the ratio of y over x. And kind of imagining that, we had this, I presented you with this diagram to kind of help imagine, well, if I'm dealing with a specific t value, and there's even the interactive unit circle, which I didn't go into, but it's kind of helpful for visualizing those points. Basically, we have a distance from this point, the initial point, to the terminal point, which is the same as the angle in radian mode, right? Because that's what radian mode was defined to mean, is what is this distance? So say, for example, we're talking about 30 degrees. That's equal to pi over 6 radians, and that would be this angle. So I'd either call it pi over 6 or 30 degrees, which are equivalent measurements. And also how we define it is, well, sine of t is the y value, right? It was the distance from, well, what is the y point at that location? Cosine of t we define to be x. But notice that that location on the unit circle is just those particular sides of the triangle. And if I'm shifting my thinking to opposite, adjacent, and hypotenuse, notice that the adjacent side to the angle is on the x-axis. So cosine is adjacent, sine is opposite, and that kind of makes sense for consistency purposes to SOHCAHTOA. The one thing that's new about SOHCAHTOA is the hypotenuse, because in our original definitions, we just had sine as y, cosine as x. There's no hypotenuse in consideration here. But actually notice tangent was defined to be y over x, which when considering what y and x are, that's going to be opposite over adjacent, right? TOA, tangent, is the y divided by x. It's the opposite side over the adjacent side. So actually tangent is exactly the same, but sine and cosine are not. But the thing I wanted to help you guys see is that on the unit circle, since it's circle radius 1, the hypotenuse must always have been 1. And that's actually what's a little simpler about these definitions, is technically sine is always y over the hypotenuse instead. So like when dealing with a triangle, it's a little bit more complex because we have this hypotenuse to take into account. But really, it all stems for like you could kind of think about this in the way of stemming from similar triangles. Because if I think about a triangle based on the unit circle approach, the hypotenuse had to have been 1. But I could think about, let's say I just expanded this triangle by blew it up by a factor of 3 and made the hypotenuse 3. What would happen is there's a property of triangles where if they have the same angles, meaning they're the same shape, you're just making it larger, those sides will all be similar to one another. So if I enlarge the hypotenuse by a factor of 3, these other two sides will also be blown up by a factor of 3 as well. So I'm not doing a very good job of explaining what I mean in terms of the connection to the SOHCAHTOA. But my point is really SOHCAHTOA is the same. These are the same rules. It's just applied to a triangle with a larger hypotenuse. Because in the unit circle, the hypotenuse is 1. And if notice that if you plug in 1 for the hypotenuse here, what you get is sine is equal to opposite, aka y. Cosine is equal to adjacent, aka x. Tangent, opposite of adjacent, y over x. It's actually the same definition. With the unit circle, we were just assuming a hypotenuse of 1. But if we have a larger hypotenuse, the sine and the cosine functions will be scaled back by the ratio of the respective side to the hypotenuse when we're extending our functions off of the unit circle. So essentially, what is SOHCAHTOA and what is the point? It is a way of using the trigonometric functions to solve right triangles when we're not on the unit circle. And so this is kind of an indication of when do I want to use it. I want to use this for triangles. I'm not saying that we're going to disregard everything we learned in chapter 4, because all of that is still helpful. It's still important to remember the basic definition of how those functions work based on the unit circle. It's just it's very different context. So sometimes you can think of evaluating a trigonometric function as by using the unit circle, but other times you can think of using it with triangles. And the context of which definition you want to use is just based on, how am I using this? So anyways, in the next video, we'll do a few more examples of solving triangles via SOHCAHTOA. See you next time.